Hello. In this video, I want to try an exam problem, which is put a box around the most acidic proton using ARIO trends. These are the 6 molecules that I want to look at. And again, the directions are put a box around the most acidic proton based on ARIO trends. And if you don't recall, you want to refresh what ARIO is. It's atom, resonance, induction, orbital, and these are trends that can help you decide which molecule is more acidic or which atom or which functional group is the most acidic. I talk about that in previous videos, number 04J20 and 40. Because when we look at the first molecule, we could take off the proton off of the sulfur, off of the oxygen, and off of the nitrogen. We want to take off a proton off of the carbon because hydrogens on carbon are very non-acidic. So if you have a chance to remove a hydrogen off of it's called a heteroatom, an atom that's not carbon or hydrogen, then most likely you'll pick one of those hydrogens, and I should say protons. All right. If you want, you could pause the video and copy these 6 and maybe test yourself. If you know these ARIO trends already, go ahead and box the most acidic proton on each of these 6 molecules, and I'll show you when you unpause the video how I would do with the problem. Okay, number 1. The key is you want to analyze the conjugate base and figure out which conjugate base is the most stable based on ARIO trends. And so I'm going to draw this a little bit odd. I am going to draw the molecule as if all the possible acidic protons are removed, and I'm going to analyze which one is most likely. Okay, so obviously this is not going to happen. You're not going to also, how many lone pairs do I need here? I need 2 lone pairs, right? And this is negative. 5 minus 1, 2, 3, 4, 5, 6. Yep. Okay. This is not going to happen. You're not going to deprotonate all 3 sites. I want to know which one is most likely. Using ARIO trends, we're going to use the A in ARIO. But remember, the A, one of the trends is based on electronegativity, and the other trend is based on size. Let's take our periodic table. Let's compare a pair at a time, sulfur minus and O minus. So there's O and there's sulfur, and the negative charge is more stable on the atom that's larger, sulfur. Interesting. So it's the anion is more stable on sulfur than oxygen because sulfur is larger. Remember, when you're comparing 2 atoms in the same group, you go by the size because that negative charge can be spread out over a larger volume. So we have a winner between these 2, meaning that S minus is more stable than O minus, and hence that SH group, the thiol, is more acidic than the alcohol. I was not expecting that, but the periodic table tells me that. This is the winner between S and O. What about between S and N? S and N. Well, this one is a little bit tricky because their S and N are in they are in different periods and different groups. You know what I could do? Why don't I compare N and O first? Between N and O, when you're in the same period, electronegativity is the way to go about. So how about this? Between these 2, comparing the 2 atoms in purple, this is the winner. Okay? Do you see that? Because O is more electronegative than N, and you use electronegativity when they're in the same period. So O is the winner so far. Now between O and S is the winner because they're in the same column, same group, and S is a bigger atom. That's an interesting problem, because now when we compare the winner between O and N, when I compare it to sulfur, sulfur's the winner. It's the ultimate winner. Sulfur beats oxygen, oxygen beats nitrogen. Ooh, we had to use two trends there, right? We had to use the atom electronegativity and the atom size. The final answer, though, is to put a box around the proton that is the most acidic. Okay, I'll draw the two hydrogens separated, so just in case you want to circle or box one of those. But we already saw, right, that the one we should box is this one. Okay. If you want to verify your answer, right, this is all based on ARIO not needing the pKa table. But if you want to check with the pKa table, the two pKa tables that I recommend are the Evans pKa table here, or the pKa table. If you can't find it in Evans pKa table, look at the UCSB pKa table. Okay, so those are your websites. I did that previously because I wanted to make sure that I'm getting these answers correct. What am I looking for? Oh. And the thiol has a pKa of 7. Alcohols around 15.5 to 16, so we'll put 16. And the amines, okay, the amines are much higher. We'll call it 36. Okay, so there, the most acidic proton off of the sulfur. Okay, we use A, ARIO. Let's take a look at this. Okay, again, same strategy. While this will never happen, I want to visualize what does both anions look like. And again, we're going to ignore removing a proton off of a carbon. And we have this, and I'm going to draw the lone pairs, and you'll see why in a sec. And we have this. Oh, interesting. Now the anion are both on oxygen, so we can't use the atom because they're on the same type of atom, same element. The next letter in ARIO is R. Let's see if one of them has resonance and the other one does not. If you take a look at this this conjugate base, we removed both protons that we suspect are the most acidic. You notice that for this anion, you can have resonance, and the resonance is this. Okay, you could push the electrons and put the negative charge on that carbon. And actually, because this is a benzene ring, you could have more resonance contributors by pushing the electrons around the ring. I'm not going to go through that. That's more, you could review your resonance notes, but phenol, right? Phenol is more acidic than what you would expect for an alcohol because it has that added resonance stabilization of the anion. This one has no resonance. You cannot move these two electrons here. Okay? Remember, for resonance, you can move a lone pair to the adjacent bond, and that's it. That's it. So you're not going to skip this lone pair all the way to this bond. And when you notice is when you put a double bond here, that carbon has 5 bonds, and you cannot resolve it. You cannot resolve it. Whereas here, that carbon initially has 5 bonds, but you can resolve it by pushing this double bond to the carbon. If you're, so let me put an X right here because that's not a good mechanism arrow. And so that oxygen cannot form resonance. But let me just complete at least what this resonance contributor looks like. Okay. And then, yeah, I'll just leave this as an anion. But do you see how the charge can be spread from that oxygen to that carbon? Hence, your final answer is this. Your original molecule looks like this. And again, we want to put a box around the most acidic proton, and therefore put a box there. The pKa of phenol is 10. The pKa of a regular alcohol, okay, that can't do resonance with its conjugate base, again, is 16. Same thing here. Let's go to number 3. 3 is interesting. I think they're all interesting actually. But 3 is we have, oh, interesting. Because all the hydrogens are attached to a carbon, and we are implying that one of these carbons is more, or one of these protons is more acidic than the other. Would it be this one? Would it be one of these two? Actually, there are 3 hydrogens here. Would it be one of these two, or would it be this one? Um, let us show, I want to show you what happens actually when we remove this proton. So this is a different strategy. I'm going to guess the middle carbon has the acidic proton, and you'll see why I guess that when when I draw the conjugate base. We do have 2 hydrogens there, so we keep one and we remove the other proton, and there's your conjugate base. What do you notice about this? This conjugate base has resonance, and you could push that lone pair to the right. That carbon has 5 bonds, so we have to resolve it by pushing the pi bond up to the oxygen. And we spread the charge to the oxygen on the right. There's a double bond there. We still have this hydrogen. You don't have to draw it if you don't want. And we have this. Now, if everyone in class proposed that this is the anion, I would say half the class would have pushed the lone pair to the left instead of the right to get the negative charge on this oxygen. Okay, we're not going to draw the mechanism arrows on the original structure though. We got to get the negative charge on this oxygen from this structure because you want to draw the mechanism arrows from the previous structure. The way to do that is you bring this back down, and instead of putting this pi bond onto the carbon with mechanism arrows or resonance mechanism arrows, you could push the pi bond to the adjacent bond. Okay? And then that carbon is messed up, but you could resolve it and make it better back to 4 bonds by pushing the pi bond up to the oxygen. 3 resonance structures, or 3 resonance contributing structures. Okay, now 1, 2, 3. By removing the proton in the middle. If I had removed this proton right here, okay, there would be a negative charge here, and actually there would be no reasonable resonance contributor. It has no resonance, would be your conclusion. Okay, so just do that on your own. Put the lone pair here and a negative charge. It wouldn't make sense to move that lone pair to the left because that carbon would be messed up, 5 bonds. It wouldn't actually make it sense to push the lone pair to make a triple bond because that oxygen would violate the octet rule. This already has 2 lone pairs here. So that fits the octet rule. You can't put a triple bond here. And then, okay, so that takes care of this. The aldehyde proton is not acidic. Okay. Over here, if I remove this proton, right, there are 3 of them here, I could have resonance into this oxygen, but I can never get the negative charge to be on this oxygen. So by removing one of these protons, there's only 2 resonance structures. The more resonance structures you have, the more stable the charge, typically. Therefore, this proton that I removed is the most acidic. And if you want to write out the answer, draw the original molecule and put a box around the most acidic proton. Now, yes, there are 2 protons on that carbon. You could remove either one. Okay, and this is, you could call it a ketone aldehyde, but this middle carbon has a proton with a pKa equal to 9. Isn't that surprising? Normally, a carbon with a hydrogen, that proton is, especially if it's sp3 carbon, that is 55, 60. In a previous video, I told you that a hydrogen off of a sp3 carbon is pretty non-acidic. Imagine if I didn't have these oxygens to provide resonance. Now that would shoot up to 55, a pK of 55. Okay. Just for kicks, I looked up the pK for this proton here. It's still better than a normal hydrogen on a carbon. It drops to 20. Okay, normally without that carbonyl group, you would think it's a 55 or 60. Okay, that's number 3. Number 4. Okay, I want to keep track of time. Number 4 is, let's see. Oh, so here again, we only have hydrogens on carbon to consider. Okay, I want to. I drew this as a trick question, but I could feel that you all are pretty bright. The trick is you see a triple bond and you see a double bond, and if you're just memorizing ARIO, you remember that alkyne hydrogens are more acidic than double bond or alkene hydrogens, which are more acidic than alkane hydrogens. But what do you notice here for this triple bond? That's not a hydrogen. That's a methyl group. That triple bond has no hydrogens, no protons. So you better not circle or box anything here. I don't even know how you would even draw a hydrogen here. There's no hydrogen on this triple bond. But there is a hydrogen, and you would be expected to draw it if you want to square it, is that one. A hydrogen off of a double bond, that's called a vinyl hydrogen, or we'll call it it's a vinyl hydrogen on the structure. But again, you're removing just a proton. But anyway, a vinyl proton or hydrogen has a pKa of, from the last video when we talked about orbital, right? In ARIA, I say ARIO, O means orbital, and we're looking at the hybridization. What hybridized orbital is that lone pair in when we make the anion? The pKa could vary a little bit, but most people would say around 45. And again, if you wanted to draw, we didn't draw the anion actually to show you the conjugate base, but it would be like that. And what you would surmise is that that orbital is an sp2 orbital. An anion or a lone pair in sp2 orbital is more stable than a lone pair in any of these sp3 orbitals or on any of these carbons that are sp3. You could go back and review why is that the case. It has to do with percent s character. The more s character an orbital has, the electrons in it are more stable. Number 5. Okay, are we ready for 5? Hopefully, those of you who are using this as a review had, before starting the video or before getting too far into the video, had circled, keep saying circled, had boxed the most acidic proton, and just double check. If you get it wrong, put an X, then put the correct answer, and then try to understand the explanation. Don't erase your mistakes. You want to know your mistakes. So don't erase it and just draw the correct answer. Put an X over your wrong answer. And I betcha that you're less likely to make the same mistake on the exam. Number 5, we have a bunch of halogens. And we have 2 amine groups. We have to figure out, and I'll go back to our original strategy. Let's put an anion on every atom that we think can lose a proton. Okay. The NH2s lose a proton each, and we have a bunch of halogens. The rule we're using in ARIO, did I use bromine? Oh, iodine. It probably wouldn't have mattered. But anyway, in ARIO, we're using induction. The I. Okay. The same atom. There's no resonance. We're up to I now. Well, the thing is, electronegative atoms like the halogens pull electrons towards it. So we have pulling away from the charge. So you could have a pull like that, a pull to the fluorine, a pull to the iodine. Okay. True. This anion is closer to the halogens, to two halogens, and the closer the halogens are, the stronger the effect. So that's really stabilizing. But also F is the most electronegative atom, so it's even pulling harder than a chlorine and iodine. So there are two things going for this. It has more halogens nearby, and it has the most electronegative halogen, fluorine. Iodine is one of the least electronegative halogens. Do you see how iodine is towards the bottom? The most is here. Electronegativity goes in that direction, to the northeast. So the answer is, let me draw the two hydrogens separate, but I'm going to remove a proton off of that nitrogen, or I'm going to indicate that the hydrogen off of the left nitrogen is the most acidic, and put a box on either hydrogen. Okay. Number 6. Okay, I want to be under 25 minutes. Number 6, oh no, this might take a while to explain. We have an amine, and now our alkyne has an acidic proton. Those of you who are memorizing the pKa table or certain pKa's, you'll know the answer because I've mentioned the pKa's for an amine and a the alkyne, terminal alkyne. But using ARIO will actually be a little bit confusing because in one aspect we have a nitrogen that has the negative charge. Okay. In another aspect, we have the carbon, and the way you draw a carbon with a negative charge, a alkyne carbon with a negative charge, sure, you could put a lone pair here and a negative charge. To me, that looks a little bit naked. I'll put a carbon and then put the lone pair and the negative charge. It's still the same number of carbons, 1, 2, 3, 1, 2, 3. According to ARIO, N minus is better than C minus because the atom is more electronegative. Remember with ARIO, when the atoms are in the same row, you go by the more electronegative. Okay? But by orbitals, the N here, that lone pair, either of those lone pairs are in an sp, what do you call it, an sp3 orbital. For over here, you know that lone pair is in sp2. So in that, oops, not sp2, sp. So in that case, sp wins, okay, because it has more s character. That votes for the carbon to be deprotonated. I know that you're supposed to consider ARIO, it's ordered this way because it's in order of importance. The atom electronegativity and size is more important than resonance, more important than induction, more important than orbital. But in this case, it's actually the alkyne that's more acidic, okay? And we're basing this off of hybridization. I guess I couldn't find a really satisfying answer for this, but I guess what they're saying is that when you compare sp3 to sp is almost always going to be the winner. Maybe we could say that. Actually, no, because if this was an OH, then that pK would be 16, and that would be the winner. Sorry about that. This chemistry is full of exceptions, full of surprises. Bottom line is, ARIO is hard to use to justify why the alkyne is more acidic than the amine. Because in that other example that I just mentioned, if I had something like this, the OH would be more acidic. So what are we going to do? The first thing we're going to do is we're going to get the answer. The answer is this dude right here. The second thing we're going to do is going to look up the pKa's. The pKa for an amine is 36. For the alkyne, the pKa equals 25. So yeah, that is the more acidic. And again, it's hard to use the ARIO rules, but we're just going to say that in this case, the orbital has a greater influence than the atom. Atom electronegativity. In here, oxygen, I guess, um, oxygen has more electronegativity than nitrogen, and now it seems that the electronegativity is outweighing the hybridization or the orbital. Because again, the pKa for an alcohol is, you'll say 16. So now this is definitely the more acidic. Okay. All right. Um, Let me give you a bonus. Um, I don't normally want to end on a one that's kind of that doesn't follow the rules very cleanly. Okay, but again, in this case, the orbital is the more influential effect. In this case, the electronegativity is the more influential effect. It happens sometimes. The bonus is this. Say what? See, something's already protonated and it's already charged. And when you have a situation like that, almost always the, the the charged atom, you would want to remove the proton off of that atom so it becomes neutral. So you'll typically want to become neutral if you have a protonated oxygen or protonated nitrogen. Again, there are going to be some exceptions, but for here, it's not part of the ARIO. Um, what do you call that? ARIO mnemonic or abbreviation, but it's based on charge. Okay, and the easiest thing is if you have a positively charged atom, that's because due to an extra proton, that's the most acidic proton, and you would put a box there. All right. Okay. Uh, if you want, give this a day or 12 hours and come back and tr you should be able to get this perfectly. Okay. You've seen the answers. See if you can also verbalize or write down the reasoning for the atoms that you box.